Hello. Do you want to cover the last week's aspects
Um,
or some of the homework thing or?
yeah, so maybe just a few words about it. So,
Okay.
um, there were two kind of take-home exercises or readings for this past week. One of them was the week one of the Coursera course, and the other one was chapter one of the hands-on machine learning book. Um, the hands-on machine learning book just reinforced the same concepts Yogesh covered in the slides last week. Just gave more examples and a few more terms. And the week one of the Coursera course, it mainly covered linear regression with one variable and the intuition behind the cost function and gradient descent, and just a little bit of the math the and the intuition there. So you can still follow along with this and the Python notebook, but everything works together. So um, if you have specific questions about any of this stuff, maybe we can take them at the end. Or feel free to jump in now. Does anybody have any questions about any of the readings from Hands-On ML or the Coursera course? I don't see anything. So it's pretty straightforward and pretty intuitive. Week two gets into, so chapter two of the Hands-On ML book does a complete end-to-end example, pretty in depth. So one thing to point out is Yogesh is going to cover really nicely how to use this with Python notebooks online, just using Google Colab. I'll share my screen really quickly. Oh, it's disabled. I'll just point it out where it is in the book. In the Hands-On ML book, if you want to use Python locally, Python notebooks, um, you
Daniel,
just
you
come.
can, I have shared the screen, so if you want, you can take over.
Okay. Let's see, share screen then. Okay, so if you want to do this stuff locally, so one is just as good as the other. If you just want to work on Google Colab, that's fine. But if you want to just run things locally for whatever reason, it's really easy. Um, uh, it starts on chapter 2, page 48 of the Hands-On ML book. Um, Takes you through installing all the Python packages that you'll need and how to use virtual environments. Okay, so it's only about 4 pages worth of instructions. So it's incredibly easy. It's not even worth really covering here and watching me type these commands. You type exactly the same commands that are covered right here. So make sure you're using Python 3. For those who don't know, there's Python 3 Python 2 is deprecated. Make sure you have pip, some Python package management tool installed. Pip is what they use here. They recommend using virtual environments, which means your projects can be and packages can be separated from one another. And then after you do that, there's just a handful of packages you need to use Jupyter Notebooks. These 6. After you install these, this is a one-line test you can use to make sure everything worked correctly. And this is all you need to type. There's a possibility if you're trying to use, one last note about this, if you're trying to use virtual environments and you just type virtual env, and it doesn't come up, it says it doesn't find virtual env, it might tell you that it's not in your path. So what you can do if you're on a Mac is do something like this. So you can add, in my case, Python is installed here. So you can, this line, what this does in a nutshell, it adds this directory, users Daniel library Python 37 bin, to the path. And the path environment variable is where the terminal looks for commands to run. So after you do that, it'll find virtual env. Otherwise, what you have to do is type in, if you want to run it, you have to type in users Daniel library Python 3.7 bin virtual env. So you have to either give it the full path or add this to the path. So just a couple notes if you want to run things locally. If not, use Google Colab, and that's the recommended way for the course. So. And Yogesh, you can take it back now.
Okay.
I have a quick question.
Okay.
Yes.
I see you are recording it. Are you actually going to upload the recordings?
Yes. So
It's
we
actually
have uploaded the recordings. Even for the first seminar, it's on our GitHub.
Oh, I didn't see it on there.
Okay, let me quickly show that aspect. So
yeah, there's a link under week 1.
So is this thing visible?
Yeah.
Okay. So the URL is, so this is the URL, GitHub URL, I think. And if we scroll down, we can see that for the week 1, there is a video lecture link, and it just points to a YouTube video.
Okay. Yeah, I went to the folder. So.
Yeah, so you should be able to, like, if you click on this, you should be able to find the YouTube video. So, and I think similarly we'll upload for today's lecture as well. So yeah, any other questions? If not, then we'll start with our contents for this week. So in today's lecture, we'll be covering regression, particularly the linear regression, and then look into like what is regression, understand the different regression types like linear regression, polynomial regression, and so on. And at the end, we will try to cover some example, how to use, first of all, how to build your own machine learning model and using linear regression. For the hands-on activity, we'll be leveraging scikit-learn Python libraries, and we'll be running all these examples on the Jupyter Notebook. So let's get started. So in today's lecture, we'll be covering the supervised learning, and the regression is a supervised learning aspect. The slides we have reference this course material from the University of Washington courses. So just a recap, last week we did cover the different aspects of the taxonomy of machine learning, like the classification, regression, and so on. So in regression, what happens is you have a set of input data. The input data has a lot of features in it. And then you have a target value, which you would like to predict. The predicted value could be a discrete value or a continuous. So in this case, it's going to be a continuous output value for the regression. So as an example of regression, we could leverage a regression technique to predict like a stock market value, right? So you have a time series data of for a given stock, and we have basically the prices of for each day or for each time interval and so on for a given stock value. And regression techniques are utilized to predict what perhaps might be the future price of a stock, say 10 years from now or a week from now, and so on. So over here, we try to predict a given continuous value of a stock from a given trend. Another example is like tweet popularity. So in this case, you might want to know like how many people how many people will retweet your tweets. So basically, you could build a machine learning model which has like for a given user, how many followers are there of that user, and then there might be a followers of followers and so on and so forth. And you might also include some of the sentiment analysis as an input to this model, and then predict how many times this particular tweet or message will be retweeted by others. So basically you can use that to estimate the popularity of a given tweet. In last class, we covered the regression and classification. So this is a small quiz to understand which of these is a regression problem. So if you read these three statements, if you can quickly type in the chat, like which of the options do you feel is a regression problem? So I'll wait for a few more minutes. So in the first case, it tells like if a project is supposed, what is the outcome of a project is going to be the likelihood of a project being a success or a failure, right? So, so you are doing some estimation over there. In the second case, you are given an image and you want to predict whether that image stands for a cat or a dog, right? And in the third scenario, you basically want to predict how many numbers of cars will be there on, say, Interstate I-40 at a given instant of time. So I see, yeah, so everybody has got a nice clarity with respect to classifying which of them is a regression problem and a classification. So the correct answer is 3, which is how many number of cars there will be at a given instance of time. So the reason behind this is like you have a continuous value. So the number of cars can change from 0, 1, 2, 3, and so on. Whereas in case of image, you can basically classify into certain types of objects, whether it's a cat, dog. So it's a distinct value that's associated. Same thing with respect to the first one. So the project could be either a success or a failure. So those are the distinct values, whereas the regression has like a continuous output. So yeah, so that's good to know. So let's move to the an example over here. So suppose there is a user who wants to sell a house, right? And to sell a house, he would like to understand how much price target does the house, how much price target he should put on the advertisement for a given house if he wants to sell that house. So what he has is like he or she has a data set which basically has inputs and outputs. So input corresponds to there is just one input right now, which is the square feet of that house, which stands for X1. So, and the output is basically the price. So the blue house over here has certain square feet, and there is corresponding value associated with that house. So like that, we have n number of houses, each with its distinct, not distinct, but each with having certain square feet and certain price point for that value. So given this input data, perhaps the user could build a machine learning model wherein he could set what the square feet area of his house is, and then perhaps estimate what how much can he set the value of the house in an ad, right? So he could leverage this data set over here to estimate the price of the house. So if we want to build a model, let's look at the data points over here. So on the x-axis, we have the input, which is the square feet of the house. And on the y-axis, we have the price. And all these blue dots that you see is basically the relation between the X and the Y, okay? So, uh, so the user has this input data set with him, and then what the user is interested is building a model so that he or she can estimate the value of the house. So in a linear regression model, so the green line that you see over here is like a relationship of yi with respect to the input function, which is the square feet. So there is, we can like correlate that, like if we draw a green line, then perhaps we can estimate what the value of the y would be for if we try to insert the corresponding values of x. So this would look like a function f of x, which is w0 plus w1 times x, right? And um, the delta over here, epsilon I, is basically telling that there is some error over here. And if we are trying to construct a line which span across all these points, then we also have to consider this epsilon I, which is an error function. So let's look more into this linear regression model. So the W0 and or W1 are the parameters of regression coefficients. So these are the regression coefficients. So we would like to understand what those values are. So the user currently only has the values of xi and yi. He doesn't yet know the values of w0, w1, and epsilon. So this is something that we would like to learn. And the machine learning model, we could leverage that to learn the coefficients of these regression model. So if we try to look into what this wi or w1 stands for, it's basically change in the predicted price for a given square feet. So it's a delta of y divided by delta of x. So that's the slope of this particular line. Now, suppose if we want to fit like a quadratic function that covers most of these points, then how it may perhaps looks like the f of x would then have like w0, w1, and then you would have a square of a given input x. So this perhaps the f of x also could be a quadratic function. And if we had to represent a quadratic function, then this would be the green line that represents that. And this can keep on going. If you have points that just span across the x and y axis, then perhaps the regression model that you could leverage is sometimes polynomial. And in that case, you just you have more than like not quadratic, but even more power function. So this covers the same, the f of x or yi, which is w0 plus w1, which are basically, if you look at, these are the parameter 1, parameter 2, parameter 3, and so on. And the xi, x2, these would be the features associated with each of the parameters. So what does, so the price of the house is not just based on a single feature, right? So you could have more features that come into picture. For instance, you could have in this particular data set, you may want to also include the number of bathrooms that you have. So how do you take that into account? So perhaps you may construct a three-dimensional figure like this, wherein you have the y-axis, which represents the price, the x-axis, which represents the square feet, and then you have the x2, another axis, which represents the number of bathrooms. So um, again, your value of price is dependent on these two um, input features, which is the square feet and the number of bathroom. And if we had to plot a plane or a function for this, then it may perhaps look like W0 plus W1 times square feet plus W2 times the number of baths. So in this case, if we want to understand what the factors would look like, is like, for instance, if we fix the value of the square feet, right? And we just want to understand if we set a given square feet value for that particular square feet, if we keep on increasing the number of bathrooms, which is the x2 over here, how will the price change? So here you can see that the 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 WI or the W2 over here would be the change in the predicted price for as you keep change in as you keep on increasing the number of bathrooms for a fixed square foot distance. So that's what the W2 stands for over here. So if we go back over here, we can see that if we fix the value of square feet and we just keep on varying the W2 or X2, the number of bathrooms, then we can estimate the value of W2 using this. Same thing applies, like if you keep on adding more features, like the number of bedroom, the lot size, year build, all these features would then be taken into account for building a model, and that would dictate the price of the house. So you can keep on adding more input variables or the input features to this regression model. So next, we'll quickly look into how we can represent this data and create a machine learning model. So basically, most of the data set, if you consider, are stored in like CSV files or Excel sheet, right? So the columns represents the input features, like feature input 1, feature input 2, feature input 3. And there could be one more column which represents a target value, so or the price that that is associated with a given input features. So while training a regression model, we will sometimes have this the whole data set associated with us, right? And then we use this data set to build a regression model, and then that model can be used to estimate the price of the house. Now, usually when you are training a machine learning model, what we usually do is, like, we may have a large amount of input data. So what so in this scenario over here, what is illustrated is that we have a input data, and we kind of split that data into a training data set and a testing data set. So the reason behind these two is that we would like to first split the data into training data sets, so that we can use that training data set to train the model. And the reason for having a testing data set is to understand how good your model has been trained. So basically, you would like to pass certain inputs to this trained model, which has been trained using the training data, and you would like to see if the values that are estimated through this training data um, by this trained model, do they actually correspond to what we are looking for? So we already know what the value is because we are using this test data set, which already has that the target value associated with it. So that's why we kind of use the training and the testing data. There is also another splitting strategy which we'll cover in the future classes. But we also use something called validation data set. So not only do we split the data set into training and testing, but we also split the data set into something called validation. We'll cover those aspects in the future class. But in this example, what it has shown is like we take the max number of data set, like 80% of the data, and use that 80% of the rows of that CSV file, for instance, and use that to train a model. And then you use the rest of the 20% to test the accuracy of that newly created model. Okay, so I think we have covered the theory and some basic understanding of the regression. I would now move on to the hands-on activity part, which is going to be Jupyter Notebook. Again, this is hosted at this link. So let me. So is this thing visible? The Google Collaboratory?
Yes, it is.
Okay, nice. So as we mentioned in the last class, there is a facility called as collab.research.google.com. So it's basically a facility wherein you can run Jupyter notebooks. So I'm just going to show how one can use this. So when we go to this link, there is an option. You may have to log in to access this, but once you log in, there is an option to open a notebook. And when you open a notebook, you can point, say, a GitHub URL. So we can use the GitHub URL that we are currently using for our class. So we can point to this Python notebook or the Jupyter notebook that we are currently using, and it is stored on this GitHub URL. So when you when we include this, it will directly go and fetch from this GitHub URL, and it sees that there is this repository. And under the week 2, there is a AI seminar week 2 Jupyter notebook. So that's how one can import Jupyter notebooks which are hosted on external URLs, for instance. If y'all want to start from scratch, then perhaps we can just go ahead and say that start a new notebook. And so it may take some time, and then you can just print like hello world, and you can run it. So once you run the Python code, you can directly execute this particular line of Python using this arrow command. And it might take a second, but yeah, so it has executed that. One can also, as shown in the last class, one can also execute Linux commands. So let's see. Yeah. Okay. So that's just an intro to the Jupyter Notebook, just a refresher again. Coming to our today's Jupyter Notebook. So here I'm just going to cover how one can use the linear regression libraries that are there, or the modules which are available in scikit-learn. So we'll be using this Python library called as scikit-learn. Um, so it's hosted at scikit-learn.org, and it's a very popular and easy to use Python library for running machine learning. There are also other libraries like TensorFlow, Keras, and so on. But for today's class, we will just try to use this one. On this website, you can find there are a lot of getting started tutorials. There are like ready to use Jupyter notebooks and a lot of documentation as well, which is regularly updated. Another good like useful thing from this website is you get to play with a lot of visualization libraries. So you can see that these are all the visualizations coming from regression, classification, and so on. And some of these are also useful, and you can understand how to plot these data sets using these visualization libraries. But yeah, so let's start with our Jupyter Notebook. So so over here, in the first case, I'm just going to be initializing my Jupyter Notebook. I have a set of import libraries which I have already defined. So we have this import scikit-learn, sklearn. So basically you just import this, and then there is a NumPy. So this is another Python library for matrix multiplication, arrays, and all the mathematical arrays and computation library. So it's a very good library for computation aspects. Then we have something called as random function. So over here, we just want to initialize the state of this Jupyter Notebook. There is a visualization library that we will be using, which is called as matplotlib, and that has a lot of different visualizations, graphs, and so on that one can leverage to plot the different data sets and for doing data analysis and so on. So right now I'm just going to be running the cell. It's not going to do much over here. It's just going to initialize the Jupyter Notebook. As you can see, it is still running. Usually it doesn't take that long, but okay. But yeah, so once this thing runs, the next thing that we are trying to do over here is basically we want to create that X and Y relationship. So this cell, what it does is it initializes the values of X variable and also initializes the value of Y variable. So again, this is a dummy data. So we are just creating X and Y values over here. And if we want to represent the X and Y values, so once you run this, it will create a graph like this. So you can see that on the x-axis, you have the you have the data points that are associated with X and Y. So it's just plotting the relationship. Not sure why it is taking so long. I'm restarting the environment over here. Let's see if that helps. Okay, I think it went through. Okay. Okay, yeah, now it is running. All right, so now that we have the value of X and Y, So this would be our input data set, right? So to use the linear regression module from the scikit, you can see it's just one line of code. So what you do is, or two lines of code. So what you do is you call this linear underscore model module from the scikit-learn, and from there you import this linear regression, and then you just initialize this model as linear reg. And for training the model, you basically just say, you just call this fit function, and you pass the X and the Y values associated with it. So once you run that, the model is now trained for this. If we if we want to see what the value of Y would be, so let's first create the two data points. So we have one test data point, which is pointing to 0. So if it is 0, it should be close to somewhere like 4, right? If our model is trained correctly. And then we have another data point for X, which is pointing to 2. So our model should point somewhere, the value of Y should be somewhere 10, close to 10. So let's run this. Yeah, and you can see, so these are the predicted values. So for the first one, it is 4.2, and for the second one, it is 9.7. Again, you can just create any kind of point. So we can say that we have 1.5, for instance, right? And for 1.5, what is the predicted value? So it shows like 8.37, and we can cross check. So 1.5. So yeah, it is showing a value somewhere over here, right? So what I want to do next is basically create more data points. So as an input, and pass that input to this linreg model, which is trained on linear regression, and just show me the value, right? So what I do is in NumPy library, there is a function called as arange. And for arange, you can say, create me an array which starts with 0 and ends at 2 with a delta of 0.02. Okay, so once you set that, it will create a series which has these elements. So 0, 0 0.2, 0 0.4, and so on, until, so let's run this. Okay, until 1.98. Okay, and we want to pass this to a function, to this linreg function model that we have trained, and we want to collect that data, right? Xtex is not defined. What is Xtex? Let's see. Okay, then we missed running that. Okay, so we ran that, and we can plot the value of the y-tex, and you can see that this was the prediction, predicted output from all these data points that we passed. So it's not perfect, but it is close. And these are the coefficients. So we can see the slope and the intercept value. So 4.215, the intercept basically corresponds to this point over here. Any questions so far?
Yes, it's Peter. Can you hear me?
Yes.
So, what is your take on feature normalization, especially when it comes to linear regression? So, feature normalization is a typical first initial step before we do any machine learning, we build any machine learning models. So how does it, or why do you think it's not needed for linear regression?
Yeah, so for feature, the normalization aspect, we have not covered in today's class, but that's a good point. I plan to cover that in maybe the next class itself.
Mhm.
Not just the normalization. I think some of the concepts, like the model metrics, we did not cover today, like the R2 score and so on. And I plan to cover that in the
Oh,
next class.
thank you. Let me ask a different question. So, do you know how the fit method for linear regression solves the problem in scikit-learn? So, does it use an analytic least squares approach? Because for linear regression you can solve it explicitly. It's just a second order problem. Or does it use a gradient descent even for linear regression to do the fitting?
Um, that's a good question. I don't have the answer right now with me. But the fit function over here is basically an abstract function, and they have tried to use standardize that across the different libraries or across the different models. So there is fit function for the logistic regression, the polynomial regression, um, across all the machine learning models in the scikit-learn.
Right.
Um, yeah.
Right. I did not want to
Yeah.
derail this discussion.
Yes. Um, any other questions? If not, I will move to this another example over here. So in scikit-learn, there are a lot of data sets that are pre-built within the scikit-learn environment or the library. So so if we want to try out playing with different kinds of data sets, then these data sets are already there on the scikit-learn. So one of that data sets today we'll try to look, which is called as the Boston housing data set. Um, the Boston housing data set basically has like different input features for a given house, and what is the output price or the medium value of that price of that house, which is also stored in that data set. So we'll try to use this data set to train our linear regression model on this, and maybe given a corresponding input, we would like to estimate what the value would look like. So again, to invoke this data set, one could run um, scikit-learn.datasets and import the different kinds of data sets that are available. So we'll load the Boston data set. Um, next, if you want to see the different features that are available for this particular data set, then we can run that. And the description of the input data set can be also invoked using this function. Again, this function is specific to this particular data set. Not necessarily you will have a variable called description associated with every data set, but this is something specific to this data set over here. We can see what this data set looks like. So here you can see that there are like 506 rows and there are 13 columns. So um, in Python, there is a library called as pandas, which allows you to do a lot of these CSV and other kind of data manipulation. It makes it really easy to use. And it has support for different kinds of like file read, file write, visualization, lot of statistics support, and so on. In pandas, there is some concept called as data frame. So data frame is like a data structure wherein you can store different values associated with it. So to learn more on that, y'all can check the pandas tutorial. But in today's Jupyter, we are just using that to illustrate how the library could be leveraged to run against this kind of data set. So first of all, we are initializing a data frame through this pandas, and we are giving input to this through this Boston.data, and we want to um, name the different columns of this data frame with this feature names. So basically you have this whole thing, right? We want to name the columns with this corresponding feature names. So once you do that, you can, we have created a data frame called DFX, and we can say that if you just want to see a snapshot of the data set, then you can give something like pda.head. So head function basically just gives the top few rows of that data set. So if we run that, we should see something like this. If we notice the feature name called MEDW, which is the median value, it is missing in this because it is not part of this Boston.data, but it is something called as Boston.target. So we have to again store the target value, which is going to be the median value of the house. So let's see what that target Boston.target value looks like. Again, it is having 506 rows, which basically corresponds to each of these input features. So we have basically 506 data points. And for each data point, you have associated value for each of these input features. And for that input features, we have the value of the median value of the house, which is stored in this Boston.target. And again, we have 506 points. So let's just create DFY variable and store all this data points inside that. This is not required. I'm just showing here for visualization purpose to just show the distribution plot of the DFY, and you can see that this is how the distribution of the median value of the house looks like. So it's in thousands. So you can see that most of the houses have like 20,000 price in this data set. All right. So there is something called D of X columns. So these would be the different columns or the feature names. And if we try to run that, then then it basically shows the relationship of each of the input features. So so here CRIM is, I suppose it's a crime rate. So you can see that the prices are low when the crime rate is high. So so it just plots the different analysis of the price with each of these features. This is again just for the exploratory purpose. But if we just want to go ahead and do the training, then as we covered in the slides, we can do something like training data and the testing data set. So in scikit-learn, there is already a function to do that for you. Otherwise, one can manually say that we would like to cover the 80% of this whole data set. So out of 506, we want some 400 points, which will be used for training the model, and the rest of the points for testing the accuracy of the model. But scikit-learn has abstracted that out so as to make it a lot easier to specify that through a function. So over here, the function is called as train, test, and split, where you could just say that we have the X and the Y, and the test data set should be 0.2. percent, and so on. So once you do that, okay, I think I have not specified the X and Y, but so this will create that, and you can see that the X train would be our training data set, which is the input feature, which has 404 rows and 13 columns. And X test is the rest of the 20% with 102 rows and 13 columns, which corresponds to the features. And for the Y train, we have 404, and the Y test data set to test the accuracy of our model, it's 102. Again, as we saw earlier, to train a model, you basically call the linear regression and then just call the fit function, passing the input and the output associated with that. So if this completes, it's taking some time here, but it should complete quickly, hopefully. Well, let me move to the next part. But once this is trained, we can do some model evaluation, and it can give you the score of the model. This will cover in the next class, but there is something called R2 score, root mean square error for this model. And here we are just trying to plot the predicted and the true value of the house. So the 20% of data that was available with us, which we want to test against the trained model, we are just passing those 20% of the known output values and trying to test it against what was estimated by this model. And we are just trying to plot them and see if there is any error. What we would like to see is we need to have a lot of points which are closer to this diagonal line that you see. So we can see that most of the points are closer to this diagonal line, which says that the predicted value was very close to the true value of that house. Okay, and then again, there are certain points which are very far away, which basically corresponds to the prediction error. Okay, and there are certain outliers as well. So that's what we see in this model. So this is how basically one can leverage the scikit-learn to train a model and test a model, do all the splitting of the input data set between the train, test, and we'll also see something called validation data set in the coming class. But this is how one can leverage to train a linear regression model. It is taking some time over here, but if y'all have any questions so far, I can answer them. Daniel, do you want to? Yeah, I think Daniel is also there to answer any of our questions. Let me restart this. Yeah, sometimes it since this is running on the Google Cloud, sometimes it might take, if there are too many people using this service, because this service is free, right? So if there are too many people trying to use this, then it may sometimes be slower.
I wanted to make sure I understood Peter's question. So Peter, you were asking why you don't need to normalize with just one feature? Is that?
No, not the one feature, but yeah, you can get away by not normalizing with linear regression. It was kind of a loaded question. You cannot get away with this with most of the other machine learning techniques. Actually, you cannot get away with normalization even in linear regression if you start doing any kind of what is it, regularization, right? So immediately when you start to punish the weights, you should not just use the raw feature values, because then your regularization will completely be bogus. See what I'm saying?
Yeah.
So this is just I would say just a very unique thing in barebone linear regression, that you don't have to do the normalization. Other than that, it's almost always. Probably the only other situation where I see you don't need it is with decision trees, but yeah, that's a completely different topic.
Okay.
Does it make sense?
Yes, but I'll have to double check on this, because I think I may have used normalization even in linear regression, but I'll have to double check on that.
Right. While you are double checking, it always confused me in scikit-learn that you can, so scikit-learn uses two different terms for normalization. The one that I like to use, and almost all the textbooks will tell you to use, is the standardization. So it's a separate step. It is in the pre-processing package, and it is called the standard scalar. Yeah, that's the canonical thing. And okay. So if you could look at not this probably this normalized too, but if you look at the fit method of linear regression and many other many other models which has every model has a fit method. In the fit method, you have an optional parameter which says you want to normalize or not in the fit method. But that normalization does a very different thing than the standard scalar does. And I burned my hands before with that built-in normalization feature. It does something different, and I probably never understood the difference. So if you spend some time with this topic, I'm interested in your take on it.
Yeah, I think that's a good point for our next class. So we'll try to use this and see how we can construct some Jupyter Notebook examples to use this normalized kind of functions. Yeah, so, that's a good question.
Yogesh, I have another very simple question, and you don't have to answer it. Anybody else can answer it as well. This is just you showed us the linear regression, and there are other things too that we probably will cover later in the class, like the decision trees or the neural networks and etc. For the linear regression itself, the question is that what are its assumptions and limitations?
Mm-hmm. Yeah, so it depends on the data set. It may not, if your data set is having a lot of non-linearity and things, we might be in a position wherein we might find other regression techniques much more useful compared to the linear regression, which may have higher accuracy. But when I'm trying to, when I have done some of these regression techniques, I usually try to play with different models and see which of the models give me the best accuracy. And based on that, I select my machine learning model. Yeah, and sometimes what I have found, my go-to, if my data set is too small, then my go-to use case sometimes could be like using a random forest and some of those models, because sometimes they give much more higher accuracy, but that's just based on the data set. if yeah, if anybody else wants to comment on this, that would be also great. Okay. Does anyone else have any questions? Um, all right. If not, then we have saved most of, I think we'll be saving all our files and the Jupyter notebooks at this particular URL, which is GitHub Balasab AI seminar. And um, we'll be continuously updating. As you can see, we also have, so we will keep on updating. We have said classification, but we can try to cover the rest of the regression techniques. Also, some of these normalization and other aspects could be covered in the coming class. There is the Coursera topic. So whatever topics that we cover during this, which are the corresponding classes or the week to follow on the Coursera website, as well as the hands-on ML book that we are also referring for this tutorial. So all these links are also there on this website. So like in previous class, we have the week 1 slides associated with it. Same thing for the week 2, we have we'll insert our slides as well, plus the Jupyter notebook. And those who might want to recap, we also have the videos associated, and you all can try to look into that as well. Yeah.
Can you give us the information of what you're planning to cover as far as the book and the Coursera course 1 week ahead? Or even
So
so you can read ahead?
yeah, so we'll hash out what are things that we'll cover in the next class by this Friday, by tomorrow or Friday. So keep an eye on this URL.
Okay, thank you.
Any other questions? Daniel?
Nope, nothing for me. Good.
All right. All right. If you all have any other suggestions, like topics that you all want to cover, please send us an email. Also, if you all want to participate in this, then please let us know. If we don't have any other questions, then thank you very much. And you all have a good day.
Thanks, Yogesh.
Yeah.